Okay, so last time we were talking about the stream team and all the factors that go with testing a stream in the state of Missouri. So again, talked about some of the factors that affect discharge. Again, that's land use, channelization, dams, and that can once again speed up the water flow and stuff like that. So cities are concreting rivers and streams to help remove water from that so the cities don't flood. How does discharge affect the stream quality? There are physical features, stream structure. So if you have a straight stream, again, the water can flow very fast and very rapid. And once again, that can create a lot of sediment to be removed and erosion to happen very fast. It can also sometimes cause flooding too downstream if there's levees and stuff that break and whatnot. Here you have a meandering one where it goes back and forth, back and forth. This can slow some of the velocity of the water down, which can allow sediments to fall out, build up, so you don't have as much erosion. Not saying you won't get some, but you will have maybe a little less. You also have the braided, which once again, you'll have like little islands or pockets filling here, and this can be sometimes in big valleys that have lots of wetlands and stuff like that. Basically, a swamp or a marsh area. So as you look at this, you can see what are called these loops that go back and forth on a river stream. If you look closely here, the river actually goes here and then loops back around and goes this way. But this part is no longer connected to the actual river. This is called an oxbow lake. So over time, the erosion eats away at that uh, soil and chips away at it to the point where all of a sudden the stream straightens itself out essentially, and it creates this oxbow lake, which is a unique habitat now. Fish, frogs, things like that can get trapped in there, and they're no longer part of the stream or river anymore. So they sometimes have very unique ecosystems or habitats that are built up within these areas. So as you look in this picture, you have this oxbow lake here. The stream is attempting to straighten itself out again right here. So it won't be long before this actually eats away and straightens itself out, creating two oxbows in the exact same area, which is kind of neat. So this is just what streams do. There's just soil, maybe it's a little thicker there, whatnot, and it causes the water to flow around. Water will take the path of least resistance. So again, you can affect the stream quality by the water flow. Many of the stream teams will test for the water chemistry, and that's a big part of water, as we know, because they issue a water quality report each year for your lakes, streams, and rivers that flow into your city reservoirs. So, chemistry of the water is very important. Is the transportation of chemicals and sediments, the concentration of chemicals and sediments within the water, and also the dissolved oxygen and temperature. So, the dissolved oxygen can again help the plant life and also aquatic life, like your fish. Temperature, again, that's dependent upon a number of factors, whether that's current rainfall, snow, ice melt, whatever it may be, can determine largely what organisms can live there. If it's too hot, yes, organisms can die. If it's too cold, it can inhibit growth, once again. So, stream teams constantly test for oxygen, temperature, and chemicals, once again. So, biology determines the habitat type and availability. The variety of velocity supports a more diverse aquatic ecosystems. So that's saying is if you have fast moving water, you'll have certain organisms live there. If you have slow moving water, you have some other types of organisms live there. If you have stagnant water, which means it's not moving a whole lot at all, you'll have another type of organisms living there, which promotes a lot of diversity. Plant and animal communities living together, once again, need a variety of these things. Biological cues, good diversity equals a good stream. So if you find multiple different types of fish, lots of different types of insects, plants, that means it's supporting a plethora of organisms, which means there's lots of nutrients, lots of good chemicals there that are not hurting or inhibiting the growth of the habitat. If it was limited to one or two things, then that's when you need to get concerned, because that means a lot of things are not able to survive in that habitat for whatever reason. Maybe it's poor oxygen. Maybe it's a chemical contamination and only the hardiest organisms can live there. So when we measure the discharge, we look at this little stream here, we can see the water flowing. The question is, how much water is actually going through this area? Okay, one of the big things that they always talk about with the stream team is your site location, trying to pick a good area to actually survey. And it's once again a relative area because again, streams and rivers can change. So that could be seasonal, even flooding can change your designated area. So you're looking for a fairly straight area that is free of obstacles. So as we look here, we got a bunch of obstacles here. We're like, probably not the best area. But this area down below, pretty good, only has one obstacle for the most part. A notable current, which means you actually have water flowing. If it's just stagnant water, probably not the best time to test or not the best area to test in. It usually has, you're looking for something with a uniform depth if possible. You're going to have variations within a couple inches, maybe even a foot or two, but you want something that's within, again, a relative comparison. So if you go from 1 foot to 8 foot, it's going to be quite a bit different. You're not going to be able to accurately gauge how much water is flowing through there from a 1 foot to an 8 foot drop off. If it was 1 to 3 feet, you got a pretty good idea how much is going through there. Discharge steps. Number one, you got to figure out the stream width. Number two, the cross-sectional area. Number three, the surface velocity. And four, discharge. Yeah, math problems. Solve it like a boss. So yeah, you got to use a little bit of math in this sometimes, measuring stuff like that. So to get the stream width, what you do is you place stakes on the edges of the flowing water on both sides of the stream. So as you can see this guy here, he's basically anchored his tape measure from one side to the other, and it's right where the water starts. Okay, only measure the width of flowing water. So you don't want to measure like the 2 feet of gravel out there. It doesn't have any water flowing through it. Okay, move any large rocks or debris obstructing the flow. But again, if it's a giant boulder, don't move it. Okay, so if you got a few rocks in there that might be slowing things down, okay, if you can handle them, move them. But if it's something large, you probably need to do a different area. Measure the stream width in feet to the nearest tenth of a foot. So this was something big that they preached, was they don't measure with the standard 12 inches. It's in tenths of an inch or of a foot. So they took a foot and divided it into tenths rather than twelfths. Why, I don't know. That's just what they use. So, but they gave me a special tape measure for it. So if you guys saw it in class, you get to use it too. But that's what we do. Okay. So the cross-sectional area, okay, is the area equals the depth times the width. So we got the width by measuring across. Now we got to figure out the depth. So the stream width determines, okay, if it's less than 20 feet wide, you measure every 1 foot across it. If it's greater than 20 feet, you measure every 2 feet. So again, they're trying not to bog you down with a bunch of data. So you measure the feet to the nearest tenth of a foot, not inches again. So it's in the tenths, not twelfths. Always stand downstream, because if you stand upstream, you're actually creating a wake around your body, which then lowers the water level in front of you. So you always want to stand downstream and put your stick that you use to measure the water in front of you. Okay? So what you're going to do is this guy would walk out there and he would go, if this was, say, less than 20 feet, he would look at his tape measure and he would go every foot and he'd have a stick and it would measure, once again, tenths of a foot rather than twelfths, and he'd stick it to the bottom of the stream, and he'd look to see where the water level hit, and he would call out to somebody recording it, and they'd write it down. He'd go to the next foot, and they'd write it down. Next foot, write it down. And what they're doing is trying to find an average of the depths, so you get basically an idea of how deep it is across your cross section here. Okay, and that will give you an estimate of how much water is actually flowing past that given point at that time. Okay, the next thing you do is you have to do speed trials. So you have to get the surface velocity of how fast the water is moving across the surface. You measure the time it takes for a wiffle ball to float downstream a certain distance. So if the stream width is less than 11 feet, use 3 velocity trials. If the stream width is greater than 11 feet, use 4 velocity trials. All right, so you're going to make a box, which I'm going to show you in a minute. So you've got your depth or your width line, and then you go upstream and you put another line. So as you drop your wiffle balls into the water, they will kind of get just below the surface of the water and kind of hang out the top too, and they'll go past the first marker, and that's when you start your timer. And then as it passes the last marker, you stop it. And that will give you basically a frequency of how fast that water is moving. Okay. So in the video with Kentucky Coffee and Sheila Wallaby, that'll be explained a little more and make a little more sense. So the water chemistry, right? So the temperature of the water affects the water density, gas solubility, chemical reaction rates, organism growth rates, conductivity, pH, and dissolved oxygen. So all those things can be controlled or influenced by temperature itself. So natural variation, seasonal temperatures, thermal stratification, ponds and lakes. We talked about that and how lakes and ponds turn over at certain times due to the fluctuating water temperatures. Once again, the cold water typically sinks. This is a great video to show you how lake stratification works and stuff like that, and shows you how all that stuff works. So give that a look if you haven't. You also have the size and temperature of the inflows, and you have artificial variation, industrial drainage, like at Thomas Hill, where they have warm water constantly being pushed out all the time to cool down that facility. So the lake down there tends to stay a lot warmer. So that's an artificial variation, once again, that can change quite a bit for a lake or stream. You have the runoff from asphalt, and once again, asphalt, it's black and it can create a lot of heat. So as the water hits it, it can actually warm the water up a bit, and again, that can go into lakes, streams, and rivers. Deforestation, once again, forests and stuff like that can hold a lot of temperature and whatnot. So if you don't have a lot of forest, you can change the temperature quite a bit. The Q10 rule. All right, so growth rates of cold-blooded organisms will double if the temperature increases by 10 degrees Celsius within their preferred range. Now, again, that is within reason. So if you go too high, of course, yes, we know it will kill them. But again, so cold-blooded organisms in really cold water, they will grow, they will prosper a little bit, but nothing like if it was the ideal temperature range. So once they get to a increased temperature, they are more active, they can reproduce more, and have better production of offspring all around. Okay? So why are frogs so happy? They eat whatever bugs them. Yeah, that's right. Dissolved oxygen. The measurement of oxygen dissolved in the water, again, is usually established by aquatic plant life or phytoplankton or zooplankton. Oxygen available for fish and other aquatic life is very important because without enough oxygen, the fish can actually die in water. A range from 0 to 18 parts per million, that's what ppm stands for. Natural systems require 5 to 6 parts per million to support population diversity, to have more than one type of organism. So having a little higher does help a lot. This varies with time, day, weather, temperature, and even plant life, and even seasonal changes too. Okay, can drastically affect it. The dissolved oxygen in winter versus springtime versus summertime and even fall will change quite a bit. So you get the oxygen solubility in water at various temperatures, as you can see here. At 0 degrees Celsius, you have dissolved oxygen milligrams per liter is around 14, but as you start to warm up, down to 35, so around 22 degrees Celsius is around 72 degrees Fahrenheit, so that's about room temperature for most people. But as you get up here, you're looking at the 80s, 90s degree range. As you get warmer, you're having less and less dissolved oxygen. Again, it can diffuse out or be used up by many of the organisms as well. pH levels determine the solubility of nutrients such as phosphates and nitrogens or nitrates and stuff like that, even carbon. Heavy metals such as iron, copper, all of which can once again be nutrients within the water too. Heavy metals more soluble in basic corrosive waters, so the pH will have to be greater than a 7. Dangerous for aquatic plant life. So what affects pH? Things like minerals, aerosols, dust, human-made waste, algae blooms, bacterial activity, water turbulence, and even chemicals can all, once again, cause problems for the pH. If you have a fish tank at home, you know that having the right pH for your fish is essential. That you may even actually have to put pH tablets or something in the water because certain chemicals that are in our drinking water or tap water can affect their livelihood. My buddy in college, he had some fish and for his little girl, and he couldn't get these fish to live for nothing. And so he finally did some reading. It turns out that he needed to buy pH tablets because the water that was in that area had a bunch of minerals in it, which threw the pH off. So as such, he had to buy these little pH tablets, and it actually saved the fish. So he was able to keep that fish for quite some time. But if you forgot what the pH scale is, you can look on the left side here, and you can see the 0 to 6 roughly is an acid, 7 is neutral, and then you get 8 to 14, which is more basic. And again, you can see the range of normal stream water is usually around like a 5.5-ish to a 7. And 7 again is the neutral. So you're getting quite a bit. But you got down here adult fish die, down here around the 2 to 3 range, and that's pretty acidic. Fish reproduction affected around the 4 range. So yeah, you're getting lots of different things going on there. But again, if you get too basic, you can have some adverse effects as well. And this is why they're also worried about things like acid rain. Acid rain can form from the burning of fossil fuels that have sulfur within them, and it comes down as that acid rain that can be very corrosive. That can affect the fish eggs, salamander eggs, amphibian eggs, whatever it may be, and as such, they just won't reproduce. They just will lay eggs, but they'll never reach maturity. So this is why many scientists are looking at the effects of burning fossil fuels beyond carbon emissions. It could be affecting the ecosystems as well. Here are some pH tolerance ranges for fish. So again, the trout can tolerate anywhere from 5 to 6.5 pH. Bass a little less, 5.5 to 6. Perches, we're looking at your sunfishes and stuff like that, like bluegill, crappie, things like that. Frogs can tolerate a pretty good wide range from 4 to 6.5. Salamanders much narrower. Clams are very narrow, 6 to 6.5. Crayfish, quite a bit of difference there. Snails, not so much. And the mayfly, which is an insect, which they have larvae in the water, 5.5 to 6.5. So again, if you get this out of whack, you're going to really devastate some populations. Alkalinity, water's ability to neutralize acid. Common natural buffers include carbonates, limestone, protects aquatic life. Natural systems range between 50 to 150 milligrams per liter as calcium carbonate. Hardness reflects the dissolved carbonate minerals, mostly of concern for drinking water and standards. So again, metals precipitate out of the solution, create scale hard water deposits. So if your glasses look like this, a lot of times it's because of the minerals or the hardness of the water. It can also cause some problems for your pipes and stuff like that, cause them to clog up. So you may be thinking, hey, my dishes are just really crummy. It could very well be just that you have hard water, and there's a special or dish detergent that you can use to actually get rid of that or remove it. But over time, it can cause etching in the glass, which permanently scars the glass. So you got to be kind of cautious of that too. Okay, but yes, you can have that cleaned up a little bit. So concentration of hardness as calcium carbonate in milligrams per liter. As you look here, the blue is the lowest, red is the highest. So as we look here around our area, we can see that we're kind of in the upper area of 120 to 180, but there's other areas in the world that are much worse than us. So as you look, they got some pretty hard water. But again, this is just showing you regional based. If you were to zoom in on a specific area, you might find that there's more red or blue depending on what type of soil is there. But just to give you an idea of what's out there. Nitrates. Nitrates, or NO3, naturally occurring form of nitrogen found in soil, formed by microbial decomposition of fertilizers, plants, manures, or other organic residues. Plants uptake nitrates. Spinach is a good sources for nitrates. Livestock, which is manure, putting that on the fields. Um, failing septic tank systems, so a lot of manure from septic tanks can also cause that. Synthetic fertilizers that farmers will go out and actually spray some nitrates on there, or ammonia, as you can see a lot of times in the springtime or fall. Causes eutrophication, though. A lot of this stuff does not necessarily always stay in the soil. The soil actually has the same charge as these nitrates, and actually they tend to leach out and push out easily into the streams, which can then, once again, cause a mineral or a nutrient bloom for the algae, and then they grow really big, and then they basically die off, and then the microbes eat it, which causes a dead zone, which is really bad for lakes and ponds. It can cause massive fish die-offs. The EPA allows 10 parts per million in drinking water, and if you were in my biology class, we talked about how places in like Iowa State University, They were trying to figure out how to reduce the nitrates in a field, and they once again dug a big hole, put wood chips in there, and they knew the microbial activity eating the wood chips. You subject them to an anaerobic respiration, they could actually use the nitrates coming through the water as uh, a metabolic process and release it as nitrogen gas, so eliminating a lot of the nitrates going into the river stream. So it was a kind of cool idea of how they did that, but again, if you want to look up some more information, I can send that to you. Phosphates, PO3, naturally PO43, naturally occurs in rocks and minerals. Plants uptake weathered out elements and compounds. Animals ingest plants, and once again, they can take it and poop it out somewhere else. So we're moving phosphates around. Water soluble, so it can be found in water. Sources: sewage, laundry cleaning fluids. Synthetic fertilizers can also cause eutrophication. Again, algae blooms, which can be sometimes really bad. So as you can see here, causing massive fish die-offs. And this is also a problem usually down by the Gulf, down there by Louisiana. We see a lot of eutrophication happening there. Hypoxia, dead zones, again, areas completely depleted of oxygen due to this eutrophication system. I would highly encourage you to check out this video. It explains a lot more on it, but there's a dead zone right down here, which basically nothing can live because there's no oxygen, and it's usually caused by high amounts of phosphates and nitrogens within the water itself, causing these algae blooms. Turbidity measures how murky the water is, estimates mineral function, organics, inorganics, soluble organic compounds, plankton, microscopic organisms. As you look in northern Missouri, we have a lot of erosion once again, so we have a lot of minerals and sediments within the water, so our water looks very murky like this. But clean tap water might look like this. You might even go to, say, southern Missouri, and the water could look more like these two, pretty crystal clear, because they have a lot more rocks, less erosion, and some of those rock streams down there. So turbidity, once again, can determine kind of what habitat is there. Relational trends of freshwater fish activity to turbidity values and time. So fish start to show signs of stress way down here when you have some of that turbidity increasing. You have fish abandon cover. Once again, increase coughing rates, reduce feeding rates, so we're seeing some problems. Reduce growth rates when we get high turbidity, and even death because they can't find anything, there's just too much, and cause some health problems for them. Okay, so too much turbidity for long periods of time can be detrimental to a population. Conductivity, the ability of a substance to conduct an electrical current in water. Conductivity determines the types and quantities of dissolved solids, commonly called total dissolved solids, or TDS. Current carried by ions, negatively or positively charged particles. So again, I guess it's just talking about what is in the water and how, again, it can carry a current. Conductivity of natural waters depends upon ion characteristics, mobility, valence, concentration, water temperature, geology, size of watershed, evaporation. Some artificial factors that can affect conductivity include wastewater, urban runoff, especially road salt, which is usually applied during the winter times, and agricultural runoff, which again can be from fertilizers and things like that. So many different things can affect conductivity, and that's something that you can also test for within your stream. And that gives you an idea of what types of minerals and stuff are there. All right, well, that's all I have for you today. So in the future, be looking for the video on how to actually do the stream team stuff with Kentucky Coffee and Sheila Wallaby. I will also be trying to push out one about birds. I just had to collect some videos of some birds so we can talk about those. So, all right, guys, thanks for watching the video. Again, do the follow-up assignment, and